All right. Thank you. Today we are continuing to talk about the Pigeonhole Principle. We will talk about Gary, the coffee fiend. We will talk about capacities of pigeonholes and a handy rule. We'll look at the problem of 99 over 7, and then we'll look at your problems, the ones that you gave to me at the end of class last time. So we'll talk about pigeons at Costco and cartons of milk and a flush of cards, etc. All right, so the first question I've got for you today is, during the year 2017, Gary drank at least 1 cup of coffee per day and exactly 500 cups of coffee in total. So at the end of the year, Gary is counting up how many cups of coffee does he drink per day. And then at the end of the year, he has 500. I would like to prove that there must be a sequence of consecutive days in which Gary drank exactly 225 cups of coffee. All right, turn to your neighbor for a second. Try and think about this.
Sequence of consecutive days.
All right. Thank you. So the question itself is tricky, right? So it's not saying something like prove that he drank 135 or 136 cups of coffee in a single day. It's just saying that there must be a sequence of consecutive days in which Gary drank exactly 225 cups of coffee. So we're not like limiting 225 to like 1 day or 2 days. There's a sequence of days. And so in that notion, the question is, I don't know, it feels a little bit misleading. So the way the book solves it is, so he drinks 1 cup of coffee a day at least. And so let's write the number of cups of coffee, like let's write a running total. So if we have A1, that's the that's the number of cups drank on January 1st. A2 is the number of cups drank on January 2nd. January has 31 days, so A32 is the number of cups that he drank on February 1st, and so on. And so we can write A1, or no, sorry, up to January 1st, up to January 2nd, up to the 1st of February, right? So he's keeping a running total of, he drinks a cup of coffee. Okay, now I've drinking 36 cups of coffee this year. And so we can write this sequence as an inequality where we have A1 is less than A2, less than A3, and so on. So exactly 500 cups. So he drinks exactly 500 in the year. And so on the left-hand side, we have 1 is less than or equal to A1 because on January 1st, he drinks at least 1 cup of coffee, maybe more. Yeah. At least 1 cup of coffee per day, exactly 500 cups of coffee total. All right, so I believe the book is structuring this like a proof by contradiction. And so the way they put it is, we desire to find integers I and j such that 1 is less than or equal to I, and then J, which is less than J, and then that's less than or equal to 365, where AI plus 225 is equal to AJ. So there's some day where after I've drinking 225 cups of coffee, I'm at this day, right? And those days cannot be the same. And so what they do next is they're like, we've got this inequality. Fun fact with inequalities, we can just add something. If we add something to all the terms, then that's still a valid inequality. So the number that we've got to work with is 225. So let's add 225 to every term in this inequality. No. Question, why are these inequalities less than and not less than or equal to?
It's,
Or go for it.
it's staying has to increase by at least 1 second.
Right, so he drinks at least 1 cup of coffee a day. What's that last number going to equal? 275. So we know that 36A through 65 is, no, not 275.
Um,
725? Okay, so now we've got 2 sequences of numbers. How many numbers are in this inequality? Like how many counts do we have as we go throughout the year? Not a trick question. 365. Yeah. How many counts do we have in this inequality? Also not a trick question. 365. We just added 225 to each of them. This number is 730. When we compare the number of things in these inequalities versus the number that we're trying to look at. So we know that each one of the numbers in any of these, so either A2 or A2 plus 225, we know that those numbers are bounded. They have to be bounded by 725. So 725 is our upper bound. And each of those numbers has to be between 1 and that number. And because we have 730 possible numbers, at least 2 of the 730 numbers have to be equal, right? Pigeonhole principle. So how about it? Can any of these numbers be equal? No, because it's strictly increasing. Can any of these numbers be equal to each other? No. So there's got to be a case that one of these, like that there's some sort of overlap between this number and some number over here, where it has to be some number plus 225. So there must be some number aj, which is equal to ai plus 225, where the book has 1 less than or equal to I less than or equal to j is less than or equal to 365. And so in this case, Gary drank exactly 225 cups of coffee between days I plus 1 and j inclusive. All right, how are we feeling about that?
Say that answer one more time.
So it must be the case that there is an I and a j such that this aj is equal to ai plus 225. So there's some day that we add 225 to get one of the numbers in that other inequality, where Gary drank exactly 225 cups of coffee between days I plus 1 and j inclusive. All right, let's talk about a theorem really quickly. Or this is more of a principle. There are two other principles I want to talk about. One of which is if one places n pigeons into m pigeonholes, and instead of just one pigeonhole, previously we're thinking that it's this one-to-one relation. But now let's say that the pigeonholes have some capacity. So pigeonholes with respective capacities. And those capacities are C1, C2, so we just label them. So up to Cm. And n, our number of pigeons, is greater than the sum of all of those capacities. Then at least one of the pigeonholes will contain more pigeons than its capacity. Right? So if I have a, let's see. If I have mailboxes and my mailboxes are all different sizes and I can fit 2 in the first, 3 letters in the second, 5 letters in the third. 2 plus 3 is 5 plus 5 is 10. If I get 15 letters, then I'm going to be stuffing at least one of the mailboxes beyond its capacity. All right. So from here, we get the principle 11.6, which is if one places n pigeons into m pigeonholes, then how many pigeons are going to be in at least one of the pigeonholes? So at least one pigeonhole will contain at least n minus 1 over m, and the floor of that plus 1 pigeons. And the reason we get this number is because of the capacities. So we have, if we say that if each capacity is n minus 1 over m, then if we have m of those, then that's how we kind of get this number. So the idea is that we take our number of pigeons, divide it by m. And so that's the capacity of at least one of the pigeonholes. All right. In any set of 99 natural numbers, there is a subset of 15 of them such that the difference of any two numbers in the subset is divisible by 7. Is divisible by 7. All right, so how do we break this down? So we've got some set, let's call it A. There's 99 things in it. And so we're looking at divisible by 7. And so since we're working with natural numbers, we can look at each number in our set and ask, what's this number congruent to modulo 7? And so we can partition into, the book uses the letter B. Again, the letter of the sets doesn't matter. But we can say it's either B0, B1, B2, and so on and so forth until 6, because a number mod 7 ranges from 0 to 6. So we want to show that the difference of any two in the subset, so any two in the subset, there's at least 15. There is a subset of 15 of them, of the natural numbers, such that the difference of any two in the subset is divisible by 7. All right, so let's use this theorem. So if we have 99 over 7, let's see what that is. 99 over 7 is 14 point something, which means if we're dividing it evenly, there's one of these 14 point something. And so one of these sets has to have at least 15 elements. So one of the sets, let's call it BI, has at least 15. I'll say we could also just use the theorem or the principle and say 99 minus 1 And then how many pigeonholes do we have? We've got 7 of them. Plus 1. So 99 minus 1 is 98. 98 divided by 7 is a whole number, which is just 14. Plus 1 is 15, and that proves it. All right, questions on that? Yes.
So we could like divide n. Wait, one second. So if n is 99 and we figured out n is 7, then we can like check what it's equal to rounding, and then check what it's equal to minus 1 plus 1 like with a floor. Like basically we can do the 99 over 7 and then take that number and
Right.
see if it's equivalent.
So these are kind of alternate solutions. So one way is where we kind of just say, okay, we're partitioning it into these 7 sets. Oh, I know that 99 over 7 is equal to 14 point something, which means that one of them has at least 15. That's one way of doing it. The other way of doing it is we have this equation. And so if we subtract 1 from 99, divided by 7, find the floor, then add 1, that gives us 15. So kind of 2 ways of doing it. Does that answer your question? Any other questions? All right. Let's go back up to my schedule here. All right, so now we get to talk about your problems.